All right. All right, Jackie. You're muted. We can't hear you. She seems like she got some technical issues. All right. Okay, I'll do it. All right. Hi, everybody. Welcome to, I think this is like our 83rd class. And we have Gabriele Vicente. He has been a presenter, what, 4 years now running, maybe?
All right.
Yeah, it's been a long time, but he's going to talk about gravitational wave astronomy. I'll let him give his background and bio and all that. So with you guys at the end, ask any questions and he'll do his best to answer those, okay? But for now, the chat is off for all you new folks because we like to keep everything with the nice security parameters. So anyway, here's Gabriele, and he'll tell you what we're going to talk about today. Welcome.
Thank you, Adrienne. It's always a pleasure to be here. So my name is Gabriele Vallente, and I'm the Deputy Chief Engineer at the LIGO Laboratory. So I'm based here in Pasadena at the California Institute of Technology. And my main job is to make sure that we are able to detect more and more gravitational waves and find new ways to use them to understand our universe. So I'm going to keep you company for a few tens of minutes, I would say, trying to explain to you what gravitational waves are and why I think they're really an important way we have now to understand and study our universe. So let's start by looking back at the past. Now, if you look up at the sky, if you're like me, you always wonder, wow, there are so many stars out there. There are so many things to see and to understand and to learn. And, mankind and humans have been like that since the beginning. As soon as they started looking up at the sky, they wanted to understand more and more what's going on. But what we can see with our naked eyes is just a small part of what is out there in the universe. So those pictures you see here, every one of those pictures is an image of our universe, what we would be able to see if we could look up at the sky and see it in the visible up here. So this is what we actually see with our eyes. But then if our eyes were like some of the telescopes we built and could see in the infrared or in gamma rays or in microwave, we would see those images of the universe. So you can see that every time we open up a new window in the universe, we learn a new way to study, to see different kind of light, we had a completely different picture of what's out there, and we learned so much more. But the amazing thing is that all the images you see here, they're all taken with different kind of electromagnetic radiation. And electromagnetic radiation is just a different kind of light. What we call light is what is the visible light we see in our eyes, but then you can move to one side of the spectrum to infrared and microwaves and radio waves, or to the other side to gamma rays and other kind of electromagnetic radiation. Well, so tonight, I don't want to talk about any way to study the universe using electromagnetic radiation, but I want to tell you how we can learn even more about our universe by listening to gravitational waves, which is a different kind of radiation, different kind of signals that are emitted by events out in the universe. And I'll tell you more about that. So I like to put this picture here. This is from Van Gogh, Starry Night, because it represents the, it always, seems like looks like a curious and very peculiar and unexpected representation of the stars. And in some sense, all of those, things going one around each other, they look to me like, almost neutron stars or stars that are moving around each other, colliding. And those waves coming out, you'll see, they will remind you of gravitational waves, the way I'll show you later. So let's get to it. What is a gravitational wave? What are gravitational waves? If you look up this in the dictionary, you find a description that is probably not very illuminating. So the way I like to understand things is to just look at the words. So we have two words here: gravity, gravitational, and waves. So let's understand those. If we start with waves, that's the easy part because we all know what waves are. So waves are oscillation, periodic oscillation, so something that goes up and down, and travel through matter or through space. So for example, right now, you are hearing me because my voice is transmitted through sound waves in air. Then they get captured by my computer that convert them into electrical waves in wires or radio that then get transmitted to your computer, and you hear me because then that is again converted into sound waves. So there are waves everywhere. And an important property of waves is that they can interfere. That means that if you have two waves that propagate and go up and down at the same time together, then they reinforce each other, and the result is a stronger wave. But if you have two waves that they are what we said in counterphase, when one goes up, the other goes down, then the sum is a net zero. And so the two waves cancel each other. And you can see it in this representation, this animation here, showing the two little balls in water going up and down, and they create waves, ripples that propagate out. When the two ripples move together and they reinforce, you get those black, strong waves. But along those lines where they cancel out, you don't see anything. The water wouldn't be moving at all there. So remember this, because interference is an important idea that we'll need to understand later when we talk about how we are going to detect gravitational waves. Then there is gravity. Well, gravity is a topic that, as you can imagine, has been very important to people for a long, long time. And I don't want to go too much into the history, but the first guy who tried to explain how gravity worked was Aristotle. That he got the idea right, that heavy things fall down and things that are lighter than the air don't fall down. But we have to get to Galileo Galilei and then Isaac Newton to really put the proper language at work. So use mathematics to explain how gravity works. But then we really need to get a little bit more than 100 years ago to this person called Albert Einstein, and I'm sure you heard his name a couple of times here and there. Einstein is the person, the scientist, who really understood the key idea of how gravity works. And his theory of gravity, which is called general relativity, is still today our best explanation of how gravity works. And the idea here is that gravity is like a geometric property of space and time. So if you imagine that the universe is a big sheet of rubber and you put a big ball with the Earth in the center, this will bend this rubber down and create kind of a hole. Then if you have a little marble, which is like the moon in this animation, that moves into this simulated universe, then the moon would like to go on a straight line, but actually going straight, since the space itself is curved, corresponds to going on a circle in an orbit around and around Earth. And so this is the way you understand gravity. Heavy objects like Earth or the sun or a star deform space and time. And then other objects feel this deformation. And although they think they would like to move in a straight line, this straight line is actually curved because space itself is deformed. So then we can put the two things together, right? So you can imagine, instead of having one star that deform space and time, you can have two stars that orbit one around each other. So the two stars will orbit, will move in circles one around each other. And then each one of them will deform space and time. But since they're moving, this deformation changes over time. So the effect is that you create ripples in space and time. Those are those gravitational waves. So when two objects like two stars or other bigger objects orbit around each other, they create this deformation of space and time that travel outward, travel outside through all the universe at the speed of light. Those are gravitational waves. And those are the things that we set up to try to detect and that we managed to detect. So now that we kind of understand what the gravitational waves are, let me go back to a few years ago to September 14, 2015, which is the day when, if you want, modern astronomy changed, because that's the day we had the very first detection of gravitational waves. So what was happening is that two black holes, and you see this simulation, this model here, two black holes were orbiting around each other. And think about those two stars that I was showing earlier. While they were orbiting, they were deforming space and time and emitting gravitational waves. But the more wave they emit, the more energy they lose. But if you lose energy, you end up falling into each other, till to the point where they fell one into the other and they collapsed and created one single bigger black hole. So that was the event that we detected as the very first signal gravitational waves. And the thing is that those two black holes collided about 1.2 billion years ago in a galaxy far, far away, and I apologize for the citation here, that was about 1.2 billion far from us. So those two black holes collided in that moment and created an incredible amount of energy. And that amount of energy went almost all of it went into gravitational waves. So this animation here shows the two black holes again, those two black balls there. And the shade of green that you see is the intensity of gravitational waves, how much space was deformed. So you see that the closer they get, the faster they move, and the more intense the gravitational wave is, till the very last moment where they collide, they merge in a single black hole, and that gives you the highest burst of gravitational waves flying away through the universe. So that happened far, far away, but this was an event so intense that the amount of energy that this explosion emitted in the tenth of a second that it lasted was generating more energy than the entire rest of the universe was generating that time in light and radio waves and gamma rays and all of that. So those are extremely intense events where two black holes collide like that. So maybe at this point, you might have the question, what is a black hole? Because I use this term, but I didn't quite explain to you what a black hole is. So let me explain that with a little bit of a little experiment here. So if you take a ball in your hand and you throw it upward, this ball will travel up and at some point will stop because gravity will attract it back, accelerate back, and come back to your hand. So the faster you throw this ball up and the faster up it's going to go. And this is the same thing that is shown here in this little cartoon. You can go on top of a mountain and shoot with a cannonball. So if you go too slow, it's going to fall close to you. The faster you shoot this ball, the more it's going to go around and around and around. At some point, if you send this cannonball fast enough, gravity will not decelerate it fast enough, and the ball will just escape forever, will never fall back. So that's what we call the escape velocity. So if you are sitting on an object and you throw something up faster than the escape velocity, that thing will never come back. So you can imagine that if you're sitting on Earth, if you were to make Earth much, much heavier, so to be bigger mass, then gravity will pull back more this object. So the larger the mass of the object, the more speed you need, the higher the escape velocity is. But also think, if you take Earth and you make it smaller, same amount of stuff, mass, but you make it smaller, then gravity will pull more because you get closer to your object. So the smaller the object is, and the higher the escape velocity. So you can imagine to start taking the Earth and making it smaller or making it heavier, and you increase the escape velocity. You have to throw your thing faster and faster and faster. But there's a but here. We know that there is a universal limit, speed limit if you want, which is the speed of light, about 300,000 kilometers per second, or about 186,000 miles per second. So it's pretty fast, but still, nothing can travel faster than light. So think of Earth and making it smaller, 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 or heavier, heavier, and heavier. At some point, the escape velocity will be larger than the speed of light, meaning that nothing, not even light, can escape that object. So how is it going to look like? Well, black, because there's no light coming out. So that's the idea of a black hole. So you can take Earth and squeeze it down, and it turns out that you have to make Earth as much as big, even smaller than a marble, like a third of an inch. if you were able to squeeze all of Earth down to 1/3 of an inch, that's how big a black hole would be. Or you can take the whole sun and make it as big as 3 kilometers. So that's the size of the black hole, the size of what is called the event horizon. So nothing, not even light, can escape if it falls inside of this. So we can't really see what happens inside the event horizon because nothing escapes. So that's what a black hole is. And back in a few years ago, we actually got a picture of a black hole. This is what is called a supermassive black hole in a galaxy called M87, which is far away, about many, many billion light years away. And what you see here is a lot of gas and stars and stuff that is falling into the black hole, and it gets really, really hot because because of friction. And this dark patch in the center is the actual event horizon. So that's dark, not because there's nothing there, but because nothing can escape from there, not even light. So the kind of black holes that we saw, and we still see a lot of them with LIGO, are smaller. They're not billions of times the mass of the sun, but they're about 20 to 30 times the mass of the sun. So what I'm showing here is the actual data coming out of our two observatories that shows the signal from the gravitational wave. So if you want, X is passing of time. So you start from left, you go to right, and time is passing. And this whole span of time here is about 2/10 of a second. So very, very fast. But then you can see in the other axis, the vertical axis, you have a measurement of what is called the strain, so the deformation of space and time. And you see that it starts with a little bit of noise, the background noise of the detector, but then there are oscillations. And you'll notice two things. Those oscillations becomes larger and larger and larger in amplitude, but they also become closer and closer to each other in time. This is because the two black holes are getting closer to each other. So the closer they get, the faster they move. And the closer they are and the faster they move, the more intense the gravitational wave is. That's why we get a signal, which is something like this called a chirp. The frequency, the pitch goes up, and the amplitude also goes up. So this was the very first detection back in 2015. After that, we had a lot of other more signals from black holes. But there's another story I want to tell you. That story happened on August 17, 2017, so a couple of years after the very first detection. And that's remarkable because that's when really we proved how gravitational waves are an important, a crucial tool in modern astronomy. And what happened there was that two neutron stars. So I'll explain later what neutron stars are, but two stars were orbiting one around each other, and they collided. They hit one the other, and they generated gravitational waves. So what I'm going to do here is play a video with some sound, and I hope you can hear the sound. So you'll hear a background noise, which is not coming freely from the universe. It's our detector. But then, as times pass by, you will notice two things. So time is passing on the x-axis, and this white line will show you where we are. You'll see that there is a line moving up and getting up and more intense in color. So it gets more intense in color because that shows you that the amplitude of the gravitational wave is increasing. It will go up because it will increase in frequency. Remember the chirp, the two objects get closer and closer, the pitch, the frequency goes up, and also the amplitude goes up. When we get close to zero, you will start hearing them, and you will hear something like a whistle changing in frequency until the two things collide. What I'm playing here is the actual data output of our detector. So this is the real sound, if you want, the real signal in gravitational waves generated by two neutron stars that collided 40 million light years away. And then those signals traveled far, far from a big chunk of the universe. Our detector heard those two gravitational waves, and then we can convert that into sound. Mind me, gravitational waves are not sound, but they're vibration, they're waves. So we can convert them into sound so that you can listen to them. Okay, listen carefully. I'm pointing to the gravitational wave signal that is showing up as a faint line here. It will get more and more visible and intense. Now you can see it very well. Listen carefully now. Did you hear that whoop at the end? Well, that's the sound of converted from gravitational waves of two neutron stars colliding. So this was a remarkable result because it was the very first time we ever detected gravitational waves from two neutron stars colliding. It was even, so this is another animation of what was happening. And the interesting thing here is that neutron stars, beside the name, they're different than black holes because they're stars. They're made of stuff. So when they collide, they create big explosions. So in this case, it was important to just alert all the other astronomers, all the other telescopes, to tell them, hey, we detected the collision of two neutron stars with gravitational waves. But if you point your telescope in that position in the sky, you might be able to see the afterglow, the explosion, the cloud of stars from the explosion. But before I show you that, because we actually saw that, let me explain a little bit what a neutron star is. And what a neutron star is basically a dead star. So if a star is more like the sun, at the end of its life, when there's not enough nuclear fuel in the core, it will become a red giant and then eventually eject some of the external part of the star, but then just cool down and become a quiet, nice little white dwarf. But if the star is large enough, then when it becomes a supergiant, it will explode in a supernova. So really think of the core of the star is collapsing and all the star, there's nothing stopping gravity from having everything collapse down. So the external part of the star will literally bounce off at iron and hard metal core of the star, and this will create a huge explosion. What's left over, there's nothing to keep that from collapsing even more. So gravity can squeeze it down as much as it wants until all the electrons in the atom are squeezed into the nuclei of the atom. And so they merge with protons and they create a big ball of neutrons. That's what is called a neutron star. So neutrons don't like to stay close to each other. They don't like to, stay too close. So if the star isn't too big, if gravity isn't too strong, then that's where the collapse will start, and you end up with a neutron star. If instead the star is much bigger, then not even that can stop, and then you get a black hole, what we saw earlier. So neutron stars are incredibly heavy and compact. Basically, you can imagine that a cubic inch weighs like 7 billion tons, basically the mass of a Mount Everest in just your spoon, right? So if you were to show the size of a neutron star on top of a city line, this is Chicago, you will see that it's about 10 miles in radius. So it's a very small star, if you want, but still as heavy as the sun or more. So the interesting thing is that after those two neutron stars collided, generating gravitational waves, think of those like two big chunks of neutrons, two big atomic nuclei. When they collided, they created a gigantic nuclear explosion. And that creates a lot of gamma ray. So what you hear now is a simulation now of the gravitational wave signal. And about 2 seconds later, the Fermi satellite, which is a telescope that is sensitive to gamma ray out in space, detected a gamma ray burst. And that was due to the explosion generated by the two stars colliding. So we saw the collision of two neutron stars in gravitational waves, and then we saw the explosion coming after that in gamma ray. But that's not all, because then with the gravitational wave signal, with our detection, we could really tell where in the sky to look. And people pointed almost all the telescope they had, and they finally discovered a new star, if you want. It's not really a star, but the big cloud of gas, super hot, that was generated by this explosion. So what you see in those two pictures is at the top, the discovery, and the arrows there point to this new point there. And you can see that that's new because a picture of the same galaxy, this black thing is a galaxy really far away. There was nothing there 20 days before the event. And instead, now there is something new. But more than that, even Hubble Space Telescope pointed to that object. And even more interesting, it pointed day after day. So the collision happened on August 17. And so you see images here going from the 22nd, it's very bright, to the 26th, it's getting dimmer, and then 28, even dimmer. And that's what happens when you have a collision that creates a gas of superheated, a cloud of gas which is superheated, and then this cloud slowly cools down because it emits a lot of radiation. Even more interesting than that, a lot of astronomers could point many other telescopes that are sensitive to different kind of light, so different wavelength, we call it light, different colors if you want. And they looked at how the color of the star, the kind of light that was emitted by this cloud of gas was changing over time. And you see that as time passes, this object became more and more red. That means that it's cooling down, but also you see each one of those bumps and peaks in these graphs that are called spectra. So to you and me, maybe they don't mean much, but to an astronomer that is used to look at that, you can recognize every single bump and every single little line, every notch there as the signature of a particular chemical element. And so it was discovered that this collision, a lot of heavy elements, but heavy meaning heavier than iron, so gold, platinum, and a lot of other elements were created. And so this was a crucial discovery because it was the first proof that most of the heavy elements that compose Earth and me and you are generated in the collision of neutron stars. Because maybe in school, years ago, they might have told you that all the heavy elements that are heavier than iron, so most of what we are made of, are generated by the explosion of supernovae. So when the stars dies and explode. And that's true. Exploding stars, supernovae, created this kind of element. But the problem is that we've been known for many decades now that there aren't enough star explosions, supernovae out there to explain all the heavy elements we see. But now with our observation and the fact that we saw that when neutron stars collide, they create gravitational waves, but also produce all these heavy elements, now we know that there are enough neutron stars colliding out there to generate, to create, to produce all the heavy elements that make Earth, rocks, plants, animals, you and I. So we are very likely what was built after, from the leftover, from the material created, generated by the collision of two neutron stars. So we have LIGO, so our observatories have been operating for several years now. And I told you the story about two particular events. The very first collision of two black holes that we call it GW for gravitational waves, 150914. So 15 is the year, 09 the month, and 14 the day. And of these two neutron stars, gravitational waves 170817. But there are a lot more signals that we observed. And this graph here shows you, pairs of black holes in blue or pairs of neutron stars in orange colliding and creating another object. So you can see we saw a lot of black holes getting as big as 200 times the size, the mass of our sun. And we saw a few neutron stars. So gravitational wave astronomy really started being a real thing only a few years ago, 8 years ago, but now it's going very strong. So, and now I guess your question is, I've been blabbing for about half an hour about the gravitational waves, but the question is, how do you really detect the gravitational waves? So here's how we do it. First of all, what does a gravitational wave do? So I told you that a gravitational wave deforms space and time. So if you imagine you have a ring of objects like marbles or something like that, or balls of planets out there in the universe that are not moving, what happens if a gravitational wave is coming through your screen? What happens is that it will look like those objects are moving in this particular way. So the distance between the objects changes due to the fact that space and time are deformed. So at some point, the objects along the horizontal will be squeezed together, but at the same time, the object along the vertical will be stretched out. And then, since it's a wave, it's oscillating back and forth, the opposite will happen. So this is a particular kind of signal that we call a differential motion, because it's different in the two directions, right? So of course, this is a huge exaggeration. A real gravitational wave creates an effect which is way smaller. So small that our detectors are about 2.5 miles long, but the change in distance generated by the first gravitational wave is so small that we would have to zoom into the nucleus of the hydrogen atom, go in, keep zooming, and then the change will be about 1,000th of the size of a proton. So this is in scientific notation, we said that that change was about 4 × 10⁻18 meters, meaning 0.0000, you put there 17 zeros and then a 4. It's like measuring a change in the distance from here to the closest star, which is Proxima Centauri, with the precision of the thickness of a human hair. So that's how precise our instruments are. So how do we do that? Well, we do that by using laser interferometers. So what is a laser? A laser is a wave, right? So imagine you have a laser that is shined into a mirror there in the center that splits the beam in two. So the two waves are equal and will propagate 4 kilometers, 2.5 miles in one direction, bounce back from a mirror, and then the other half of the wave will go on the other side, another 4 kilometers, 2.5 miles in the perpendicular direction, and they will come back. If the two distances are exactly equal, the two waves can come back in counterphase and cancel each other, so you don't see any light. But now if a gravitational wave comes by, it's going to make one of the two arms longer and the other shorter. So one wave will come back a little bit later and the other will come back a little bit earlier. But then they cannot cancel perfectly anymore. So some light will leak through and we can see light there. So this is how interferometer works to detect gravitational waves. It takes a very small deformation on space and time and convert them into change of light in our detector. And this is how the little thing looks like for real. So here you're flying over the Hanford detector up in Washington State. So in the center there, that building you saw is where the beam is split in two. So we have that concrete beam. Now we're looking at another detector, which is in Louisiana, Livingston detector. So again, the laser and the beam splitter are in that big building. And then the light propagates for 4 kilometers inside a vacuum tube to get the air out to avoid any disturbances, and then gets to the end station and be reflected back. So this is an animation showing you what a laser would look like. And soon you'll see footage from the inside of our detector. So every one of those big tanks contains one of our mirrors. And all of that, all the air is taken out to avoid vibration and disturbances. And now you see back again the detector of Hanford in Washington State. So as you can imagine, there's a lot of technology going into making those instruments so sensitive. So as I already mentioned, that all our systems and mirrors are kept in vacuum. They're kept in vacuum to avoid contamination because air and dust and all of that, but also because vibration in air, sound, will generate changes in the distance that are way bigger than what we try to detect. Our mirrors shown here called core optics, they're big chunks of ultra pure glass with coatings on the top that reflect 99.9995% of the light. All those mirrors, of course, we can't really see them on ground because ground is always shaking because of small earthquakes. But we need to have them suspended to pendulums to isolate that motion from the motion on the ground. It is all kind of technologies that went into, getting to the sensitivity that we actually got. So going back and concluding here, now gravitational waves are really a part of what we call multi-messenger astronomy, because now we are not only able to look at the sky using electromagnetic waves, light, radio, etc., but we can also look at the sky using gravitational waves. We detected an incredible amount of black holes colliding, much more than were expected. We detected those two first neutron stars colliding, And I explained to you how that made us discover that the collision neutron stars is what generate this short gamma ray burst and what produce almost all the heavy elements that are part of most of the universe as we know it. So of us, of Earth, and everything. So where are we now? Well, Advanced LIGO, which is the detector working now, has been back since May observing the universe, meaning where we stop tweaking, we stop trying to improve it, and we just turn it on and listen. So far we had like 21, oh, that's a typo, 21 days, not 12 days, apologies for that. And we have 120 days, sorry, that's the problem. So since May, it's about 120 days, yeah. So we had 41 detection, 41 new signal from binary black holes in 120 days. So more than one event every 3 days. And so, you know, we started back in many years ago in 2015. And in the first time we were observing, in 100 days, we observed three collisions. Then during the second time, we observed 8. During the third time and the fourth time, we were detecting, we were observing the universe, we observed 44 and 35. Those numbers get bigger because me, together with all the other scientists and engineer, we invent new ways to improve the sensitivity of the detector, to be able to reach farther and farther away into the universe. And so the more we improve the detector and the more events we can detect. So up to today, we had a total of 131 signals from gravitational waves. So that's really a lot of events that we have observed into a little bit more than a couple of years of total time observing the universe. So if you're interested, there are ways you can be alerted every time we have a new gravitational wave detector. You can get a little notification on your phone saying, hey, LIGO detected a new pair of black holes colliding. And we have 2 apps. One is called Chirp. You remember, Chirp is the name of the signal generated by the collision of objects. And the other one is GW Events, and you can find them in your favorite app store and install on your phone. Or if you prefer to use a computer, you can go to this website, gracedb.ligo.org, and you can see a list of all the events that have been detected. So that said, we are observing, as I speak now, the 2 LIGO detectors are on and listening to gravitational waves coming from the universe. So we expect a lot more detection in the coming few years, because our observing run number 4, which is going on now, will continue for all of this year and for all of 2024. So if in 120 days we detected 41 collisions of black holes, you can imagine how many more we will detect in the year and a quarter that we have left. Why are we stopping after the end of 2024? Is because even as I speak, me or the other engineer that work with me are working very hard to come up with new ideas and new ways to improve the detector. So it's always a race between observing more signals, then stopping, improving the detector, so you can observe even more. With that, I conclude. I'll leave you with this slide where you have a few pointers and information where you can go if you want to learn more. You can go to our website, ligo.org. And of course, we are on Facebook, Twitter, YouTube, and all the social networks that you all like. Thank you for your attention. And if you have any questions, please feel free to ask anything.
All right, I'm getting ready to put the chat back in. Anybody have any questions? Let me see, make sure I could, yeah, unmute and write in the chat. And while they're thinking of questions, I have one. How much of the sky are you guys able to detect? And I'm not sure how that's measured.
Thank you. So it's easy to measure because the answer is basically all of it. That means because our telescopes, our observatories, they are sensitive essentially to the entire sky all at once. They have only a few regions in the sky where they're not sensitive at any time. So that's the reason why we want to have two detectors. So thank you for the question, because I didn't mention that. So why having two detectors? Isn't that enough? Well, only one detector. The positive thing is that it can see signals coming from any direction in the sky, but at the same time, you can't really tell from which direction it's coming. So having two means that we can play the same game that the brain plays with our two ears. Ears are the same, right? You can't point them, and they're sensitive to sound coming from basically every direction. But then our brain is able to measure the different time when sound arrived to our two ears. And by that difference, our brain is able to tell if the sound is coming from your left or from your right. So we can do the same with gravitational waves. We can do something which is called a triangulation. So we actually measure the different times when the signal arrives to two, ideally three detectors, and that gives us an information of where they are in the sky.
Thank you. Good
So I
information.
see you.
Any other questions? When will something big hit the earth?
We don't know. Hopefully never.
I know. How have gravitons ever been detected?
So here is so we don't really know what gravitons are. So if you think of gravitons as gravitational waves, then yes, we have detected a lot of them. So, but gravitons are supposedly the particles that make up gravitational waves, the same way that photons make up light. So no, we have never detected directly a single graviton. We don't even know if it exists because we don't have a way to explain how gravitational waves behave at the quantum level, which is what we would need to detect and understand what gravitons are. So it's another very good question. Does astronomy workers work 24/7? No, we are humans after all. So we do normal 8 hours or maybe a little bit more sometimes. But for example, at the beginning of our last observation run, we had shifts. So at any time, there was always an operator that was in charge of making the instrument work. And so we had shift of 8 hours. So there was the operator that started in the morning and afternoon and then evening. Now we don't have 24/7 operators on duty because we automated a lot of our detectors. So during the night, the detector works by itself. So unless there's an emergency, there's no need for somebody to be there. Let's see. Is there anything that is able to exit a black hole? We don't think so. So if black holes behave the way we believe, then to escape a black hole, something should travel faster than light, and that's not possible. So as far as we know today, nothing can escape a black hole. Are gravitational waves detected at a certain frequency? Yes. So gravitational waves could be emitted potentially at any frequency. So frequencies are how many oscillations per second you have. So where two black holes are far away, they move slowly, so they would emit gravitational waves of very low frequency. And then the frequency of the signal increases with the passing of time, and the closer they get, the faster, the higher the frequency get. So we are able with LIGO to detect the gravitational waves only in a specific band between 10 hertz up to maybe 10 kilohertz, so 10,000 hertz. That's not because gravitational waves exist only at that frequency, because that's our detector is built in such a way that it's not sensitive out of that. It's like, you have a camera that see only visible light, cannot see infrared, cannot see other kind of lights. Are there tiny black holes that can't affect us? Well, this is an interesting thing about black holes that was predicted by Stephen Hawking several decades ago. Black holes evaporate over time. So they emit a little bit of particles. And the funny thing is that the the smaller they are, the faster they evaporate. So tiny black hole would live only for a fraction of a second. So there aren't tiny black holes there because they would evaporate before they can get anywhere. Are black holes a threat? Not directly to us. We are pretty sure that there aren't any black holes nearby, especially because if there was a black hole somewhere near, we would, even if we don't see it, we would feel the gravitational pull from that black hole. So we would see, for example, that planets that don't move as expected. We don't see that. Of course, if there were a black hole nearby, that would be a problem, but there aren't. Okay, what is the smallest black hole? So there is. So if you remember when I was showing how the black holes, how the stars dies, right? If the star is too small, then gravity is not strong enough to collapse the star into black holes. So if the star is smaller than twice the size of our sun, what you get is a neutron star. You can't generally make a black hole smaller than that. So you need to have to be a black hole, the star needs to be at least twice as big as the sun. So that's the smallest black hole you can make. Can observing gravitational waves help us understand dark energy and dark matter? Absolutely, yes. And that's one of the most exciting things in this field, for me at least, especially dark matter. Because, dark matter is something that we need to explain how the universe behaves, and it's matter. So we need the mass. But it's dark, it doesn't emit any kind of light. So what is an example of something that has abundant mass but doesn't emit any light? Black holes. So maybe black holes can explain dark matter. Also, we know that dark energy is, when a physicist talks about dark something, it's just a way to say, I don't really know what it is. So dark energy is something that we added kind of ad hoc to our theories to explain what we see in the universe, but we don't really understand it. So it's possible that there is something just a little bit wrong with our idea of how gravity works. And that is something that we might be able to discover when we observe black holes colliding, because we see deviation from what we expect from our theory of gravity. And those deviations might give us a hint of what's hiding behind, what's the next step. Would anything happen if a black hole was really close to Earth? Well, it depends how close, right? So if it were somewhere nearby the solar system, it would start attracting planets, and then would start perturbing the orbits of the planets. So it will disrupt all the motion of the planets in our solar system. If the black hole would even be closer, then you would Earth and all the solar system will eventually fall into the black hole. So yeah, you wouldn't want to have a black hole too close to us. What is the biggest black hole recorded? So here, let me answer in two ways. So the biggest black hole that we recorded with LIGO, so emitting gravitational waves, was about 200 times the size of our sun. So a pretty big black hole. But we know that at the center of every galaxy, we believe there are supermassive black holes. And those are huge black holes that have a mass of more than 1 million or hundreds of million times the sun. And we think that those are black holes that grew over time by feeding on more and more stars. What would the inside of a black hole feel like for a human? So here's the thing. The idea is that if you were falling through a black hole, even way before you get to the inside, you will be stretched. What some people call spaghettification, because you will turn into like spaghetti, because as you get close to the black hole, your feet will be pulled more than your head. And so you will become very, very long and thin, probably very uncomfortable too. And so you would be long unconscious and gone before you actually enter the black holes. But the interesting thing is that even if somebody managed to get inside the black hole, it's not possible to come out. So we will never know what it is inside. All right. What made Sagittarius A? So that's the big black hole at the center of our galaxy. And as I mentioned earlier, we believe that that was generated by a smaller black hole that kept eating the stars nearby, and it became very, very big. Wow, a lot of questions here. All right, let's move on. How many employees are in your organization? So I'm part of the LIGO laboratory. So LIGO stands for Laser Interferometer Gravitational Wave Observatory. So we have four locations: Caltech, the main base. We have a group at MIT, which is another university in the East Coast. And then we have the two observatories, one in Washington State and one in Louisiana. In total, we have about 200 people, a mixture of physicists, engineers, technicians, and many other skill sets that are needed for this. What role do gravitational waves play in the universe? Well, that's part of the many kind of radiations that are emitted by objects in the universe. So they play the same role as light, radio waves, and all of that. So for us, for humans, since we are curious to understand our universe, it's just another way that we can use to understand how our universe works. What is dark matter made out of? We have no idea. There are many hypotheses. None of them turn out to be confirmed. So we don't know. That's the only answer to that question.
So, Gabriele, for the last 5 minutes or so, if any of these students want to become a gravitational wave scientist, what would they have to do? What classes would they have to take?
Great question. Thank you. So, as I mentioned, there are a lot of skill set and a lot of different roles in our organization and to contribute to make a gravitational wave observatory work. If you want to become a gravitational wave astronomer, then you have to study astronomy, which is a branch of physics. So you will need to learn how physics works, math. Of course, math is a very important part. But to build a gravitational wave detector, we need a lot of different engineers and skill sets. So we have, in my group, I have electronics engineers, or mechanical engineers, or vacuum engineers. So a lot of different skill set. But it's you have to study, along a STEM subject. So some science, technology, engineering, and that.
All right, thank you. Any more questions? Got a few more minutes. I have one. Oh, thank you. Thank you.
You're all very welcome. It's always a pleasure. It's one of the best crowds.
Yes, it was. You guys were excellent. Thank you so much. It saved us a lot of stress. And I got to listen in for a change, right? Somebody says, do gravitational waves disrupt our
Electronics?
electronics?
No,
Yeah.
the effect of gravitational waves is so small that I think it changed the distance between our two mirrors that were 4 kilometers apart, so 2.5 miles, by a fraction of the size of the nucleus of an atom. So they don't have any effect on any of our system. Actually, it's extremely difficult to detect them. That's why we have to build these complicated and huge machines.
All right. So guys, I'm waiting to hear back from Mr. Stokes, because I want to bring our technology event to Suzanne this year. So I'm waiting to hear back from Mr. Stokes. So tell him, say, hey, you need to reply to Miss Atkins, because Gabriele is going to be a presenter wherever we go this year again, right? And I want to bring it to you middle school kids this year instead of the high school. So more to come on that. But we like to thank Gabriele for giving us an hour of his time, because he's a really busy guy. And I appreciate you guys for tuning in. It was 50 of you guys, I counted, and I have all of your names. He's on rotation, so we'll see him again in the next 6 or 7 months. And we all appreciate you, and we appreciate you, Gabriele, and we'll see you soon, right?
Thank you. It was a pleasure.
Yeah.
And everybody have a nice weekend.
Yes. Everyone have a great weekend and be safe. Thank you.